Now, let's try to solve the part C of the question where we are supposed to prove that theta is equal to pi by 5 and 3 pi by 5 are the solutions of a given equation. So, how do we do that? If we observe the answer to the part B in the right hand side, so observe the right hand side and this particular expression. So, you will observe that if you take sine theta as common in this entire term, we will get this entire expression. So for part C, we are supposed to prove that there are two values of theta which are given to us. Those are the two solutions of this particular equation. Hence, we are supposed to prove that this entire expression of 16 sine 4 theta minus 20 sine squared theta plus 5 should be equal to 0 if you put theta as pi by 5 and 3 pi by 5. In the part B, we had found out the expression for sine 5 theta as this. Now, as discussed earlier, on the right-hand side, if we take sine theta as common, let's write sine theta, and in the bracket, we will get 16 sine 4 theta minus 20 sine square theta plus 5. And this expression in the bracket is the same one which is given in this equation. And on the left-hand side, we have a sine 5 theta. Now, what we are supposed to prove is if you put theta as pi by 5 and 3 pi by 5 in this entire bracket, that should end up to be 0. That is what we are supposed to prove. So how do we do that? First, put both of these values on the left-hand side. What is the value of sine 5 theta when you put theta as pi by 5 and 3 pi by 5? So let's see. Sine 5 theta will be equal to sine of 5 multiplied by the first value of theta is pi by 5, which simplifies to sine pi, which is equal to 0. Similarly, let's find out sine 5 theta when the value of theta is 3 pi by 5. So if we simplify this, we will get a sine 3 pi, which is also equal to 0. Hence, we can easily say that these two values, pi by 5 and 3 pi by 5, are the solutions of sine 5 theta equals to 0. Now, let us make this entire bracket as the subject. So let's see. If I write down 16 sine 4 theta minus 20 sine square theta plus 5, that will be equal to sine 5 theta divided by sine theta. Now we already proved that the value of sine 5 theta is equal to 0 at those two values of theta. Hence sine 5 theta is equal to 0. Now we need to be very careful that we have a sine theta in the denominator, and the denominator can never be 0. Hence, we have to be careful that sine theta should not be equal to 0 at the two values which are given in the question. So let's see. If we write sine theta when theta is pi by 5, sine pi by 5 is definitely not 0. Similarly, sine 3 pi by 5 is definitely not 0. Hence, we can say on the right-hand side, the numerator is equal to 0 and the denominator is not equal to 0. Hence, 0 upon something not 0 is 0 itself, which means this entire expression on the left-hand side will amount to 0, which we were supposed to prove. So this entire equation is equal to 0. And that's how we solve the C1. In the second part, we are supposed to prove, hence show that sine pi by 5 and sine 3 pi by 5 is equal to root pi by 4. So how do we do that? We already proved this expression, which is 16 sine 4 theta minus 20 sine square theta plus 5 is equal to 0. So to simplify this quadratic, let's take sine square theta is equal to t. Hence, we can write this expression as 16t square minus 20t plus 5 is equal to 0. Now, in the part 1, we already proved that pi by 5 and 3 pi by 5 were the solutions of this particular equation, which means we can write the two roots of this equation will be sine square pi by 5, that's the first root, and the second root is sine square 3 pi by 5. Now, if you go back to the question, we are supposed to find the product of sine pi by 5 and sine 3 pi by 5. So now let's analyze this quadratic with the two roots. Now we know the basic formula for quadratic, which is ax square plus bx plus c is equal to 0. So if a quadratic looks like this, then the product of the roots is given by c by a. So let's say if alpha and beta are the two roots of this equation, so the product alpha beta will be equal to c upon a. So in this equation, the c constant term is a 5 and a is the coefficient of x square, which in this case is t square. So the value of a is 16. Hence, we will write the product of these two terms will be equal to 5 upon 16. Hence, let's write sine square pi by 5 multiplied by sine square 3 pi by 5. That is equal to 5 upon 16. Now, in the C2 part, we were supposed to find the product of sine pi by 5 and sine 3 pi by 5. So it doesn't have a square in it. So what we will do is we will take the square root on both sides of this expression. So before we do that, sine square pi by 5, we can write as sine pi by 5 whole squared multiplied by the second term will be written as sine 3 pi by 5 whole squared. That will be equal to 5 upon 16. And now, if we take the square root of both these expressions, the left hand side as well as the right hand side, on the left, we will get sine pi by 5 multiplied by sine 3 pi by 5. And on the right hand side, we will get a root 5 upon 4. And this is what we were supposed to prove. And that's how we solved the C2 part of this question. So the complex number given here is W is equal to IZ plus 1. Find W when two parts are given. Z is 2I and Z is 1 plus I. So this is fairly straightforward. All you need to do is put the value of Z in the equation of W. So let's try. W is equal to IZ plus 1. In the first case, Z is equal to 2I. So if you put 2I in place of Z, W will become 2I squared plus 1. Now, since we know the value of I is root of minus 1, so I square will be minus 1. Hence, the value of W will come out as negative 1. That's the answer for the first part. In the second case, we put 1 plus I in place of Z. So let's do that. So W will become I times Z, which is 1 plus I plus 1. Let's simplify this. If you open up the bracket, we'll get I plus I square plus 1. And we know I square is nothing but minus 1. Minus 1 and plus 1 will get cancelled out. Eventually, we just get W is equal to I as our answer. So this was pretty straightforward. Now moving ahead to the second part of the same question. So have a look. So the same complex number, main data is still the same. Point Z on the Argand diagram can be transformed to W by two transformations. So we have to describe which transformations do we need to make that happen. So now to understand this, remember the logic of multiplication of any complex number with I. Because see what has happened here, because they have given Z is a point. From Z, you have to transform it to W. W is IZ plus 1. So how do we go from Z to W? Step 1, we multiply the complex number with I, and then you add 1 into it, right? So step number 1 is multiplication by I. So the logic is, which you need to remember as a concept, multiplying a complex number with I rotates it anti-clockwise by 90 degrees. Let's understand that using a diagram. So if you have a complex number, let's say is in the first quadrant, and if you multiply that with I, so the complex number will rotate itself by 90 degrees. So let me draw. As you can see, IZ is in the second quadrant in this case because it has rotated by 90 degrees anti-clockwise. Now, if you multiply by I one more time, which means IZ squared, so it will rotate one more time by 90 degrees. So what that means is, if you multiply by I again, you should get I square Z. This is formed if you rotate the IZ by 90 degrees one more time. Now, this should be fairly easy to understand because the value of I square is minus 1. So what we have found actually is minus Z. Negative Z basically is the same complex number, but in the opposite direction. So we have reversed the arrow. But the logic to understand is if you multiply any complex number with I, the rotation will happen by 90 degrees. Now back to the question. We want to go from Z to IZ plus 1. So let me first of all show you what the marking scheme, how the marking scheme is presented for this. So have a look. In the marking scheme, this is the official answer. So first they have written rotation of 90-degree anti-clockwise. That is because we are multiplying by I. And then they have said a translation of 1, 0. Now, as we know, let's understand this particular representation 1, 0. If your complex number is A plus IB, this is the Cartesian form. We can also represent it like this: A, B in a column notation. This is called the column notation of a complex number. So that's what they mean. Let's understand the logic one more time. We started off with Z. Step one is you multiply the complex number with I. That's the step one. And step two is you need to add a 1 into it. Now remember, in complex numbers, whenever you have a real number, so 1 is a real number, right? So in complex notation, you can write that as 1 plus 0I. So this notation is 1, 0 in the column form, right? So that's the answer, the official answer key: rotation 90-degree anti-clockwise followed by a translation of 1, 0. But to understand this in depth, let's draw a diagram. Now, let's say if I randomly draw a complex number Z in the first quadrant, if you multiply by I, so the complex number will rotate by 90 degrees. So let's do that. So this is your new complex number, which has been rotated 90-degree anti-clockwise direction. Now we need to add 1, which is 1 plus 0I. So which means the real part will be increased by 1, imaginary part stays the same. So whenever you have to add a 1 and 0, all we need to do, we go 1 units towards the right. So let me repeat, this was your IZ. You need to go 1 units to the right hand side on the real axis. And on the imaginary axis, there is no transition because imaginary coordinate is 0. So this particular point, let me draw that as well. We are considering this point. If I connect it with the origin, so this particular point will represent IZ plus 1. So all of this diagram which I have made is just for your understanding. The answer, the question was describe the two transformations. So we write rotation of 90 degrees, second, followed by translation. That's it. That will be the answer, and you will get 3 marks for that. No need to draw the diagram.